Hello guys, so this lecture will cover regression with a single regressor. Hypothesis testing and confidence intervals will be the main things that we'll be covering in this lecture or in this chapter. So let's take a look at the different things that we'll be covering. So the outline or the checklist for this chapter is that we'll be covering the standard error of the beta 1 hat that we actually estimate through the regression analysis through the OLS method that we outlined in the earlier chapter. And then we'll actually be doing hypothesis testing concerning the beta 1 hat that we actually find. So our aim is to basically find out whether we have some sort of confidence or a level of confidence in the estimator beta 1 hat that we actually found out through the OLS regression analysis. Once we do that, we can also come up with the confidence intervals for beta 1, which is beta 1. Remember, the beta 1 without the hat on it is the population estimator, and beta 1 hat is the sample estimator. So confidence intervals for beta 1, the population estimator, can be calculated and we'll show the techniques in this lecture for doing that. We will also cover regression when x is binary. So far what we have looked at is when x, the x variable, the right hand side variable or the independent variable, was a continuous variable. But now we will also take a look at how things actually change but kind of also remain the same when x is a binary variable, which means it is a dummy variable. We will also deal with issues of heteroskedasticity and homoskedasticity and how this additional assumption of homoskedasticity can be combined with the three earlier assumptions of OLS as to make it more restrictive. And we'll also take a look at the efficiency of OLS and the student t-distribution. What is the efficacy of the student t-distribution when it comes to small samples and when it comes to larger samples. So these are the different things that we'll be covering. So a big picture review of where we are going. So we have to do a number of things. We have to kind of do them in a chronological or a logical order in order to actually have some sort of confidence in our regression analysis, the estimator that we actually estimate through the regression analysis. So number one, we need to state the population object of interest. So remember that in the previous lecture, we were looking at the example of how class size can affect test scores. So the economic theory underlying this analysis was that smaller class sizes will mean that there is more attention on every student, which will basically increase the average test scores in the classroom. So the population in this case is the total number of schools in the District of California. Number two, provide an estimator of this population object. So once again, so the regression analysis or the OLS analysis is the process through which we actually obtained an estimator for this population. We did that in the earlier chapter. Now in this chapter, we will actually focus more on the 3, 4th, and 5th aspect. So number 3 is derive the sampling distribution of the estimator. This requires certain assumptions. So sampling distribution of the mean was covered in one of the earlier chapters. So this process is very simple even in the case of the estimator beta 1 hat, and the underlying assumptions remain the same for sampling distribution, as in we will still be taking advantage of the central limit theorem and law of large numbers when we are doing this. The square root of the estimated variance of the sampling distribution is the standard error of the estimator. So standard error of the estimator will be calculated in this lecture, and I'll show you how to do that. There's a formula for it, and it is important to do that because standard errors will be used, the standard error of the estimator will actually be used to actually come up with the t-stat, and with that t-stat we will actually find out whether the coefficient is a significant coefficient or not. And we can also use the standard error to construct t-statistics and confidence intervals. So that is component number 5. So the t-stat will be used for hypothesis testing, while confidence interval will basically tell us how much confidence do we have in the range that the true population estimator lies within that range. So the object of interest is beta 1 in this equation shown over here, right? And this equation is pretty much the same as from last chapter. We have the dependent variable y, we have the constant or the y-intercept signified by beta naught. We have the beta 1, which shows the relationship between x and y, and we have the error term over here. So beta 1, just like I said, shows the rate of change of y over rate of change of x. So kind of like the slope of the straight line, which we are estimating through the OLS analysis. So sampling distribution of beta 1 hat. To derive the large sample distribution of beta 1 hat, we make the following assumptions. What are the assumptions? We have already gone over these 3 assumptions before, but I will just summarize these for you guys once again. So the number 1 assumption is that the expectation of u given any x is actually equal to 0. And why is this important? It's important because if that is not the case, then we can say that that u will actually, the expectation of u will be different at different levels of x. And so for example, if I give you the example of the example that I used in the previous lecture. So the example that I gave previously was that if we take a look at the relationship between class size and student-teacher, if you take a look at the relationship between student-teacher ratio and test scores. Now, if you think about this, people are not assigned a school with the student-teacher ratio randomly. So there might be some underlying characteristics of the population which is served by different schools. So in a sense, the expectation of u given any x, and x in this case will be the student-teacher ratio, will not actually be 0. Now, assumption number 2 is that x and y are independently and identically drawn. This simply means that when we are selecting a sample of schools to actually see what their average test scores are and what the student-teacher ratio is in that school, there is no effect of choosing the next school from the previous school. So what it means in simple terms is that if the last school that I choose is school number x3, so choosing school number x4 will have no bearing on what I chose for x3. So it means that they are independently and identically drawn. So this is more of a problem when we are looking at time series or panel data, because we are actually looking at the same schools for over a number of different time periods. And for example, if you are taking a look at the relationship between unemployment and GDP, unemployment in the previous period will have a lot of effect on the unemployment in the current time period. So in that case, the x and y will not really be independently and identically drawn. But whenever we are taking a look at cross-sectional data, this is rarely a problem. Assumption number 3 is that large outliers are rare, and this is simply shown by this assumption over here that the kurtosis of x and the kurtosis of y is less than infinity. So if you remember, kurtosis basically measures the thickness of the tails of the distribution. So if the kurtosis is not infinity, is actually less than infinity, then it would mean that there are no large outliers in the sample. So when all 3 of these assumptions are fulfilled, it means that we are actually holding the least squares assumptions. Alright, so sampling distribution of beta 1 hat. So under the least squares assumption for n, when n is large, when the sample is large, beta 1 hat is approximately distributed like this. So what this simply means is that the mean of the distribution will be beta 1, which is the population estimator, and the variance will be given by this formula over here. So if you see over here, there's a V over here. So this is the variance of V. And what is V? V is actually Vi is equal to Xi minus mu X multiplied by Ui. So hypothesis testing is very important when it comes to the estimation of beta 1 hat. Why is it important? Because we want to feel confident about what we estimated, that the estimator that we have actually calculated with the help of OLS while working with a sample that we got from a population. So that estimator, we want that estimator to be as close to possible to the population estimator. And in order to see whether we are confident in saying that it is very close to the population estimator, we actually do hypothesis testing. So the general setup for a two-sided test is that the null hypothesis will be that beta 1 is equal to the hypothesized population estimator, versus the alternative hypothesis, which is that beta 1 is actually not equal to the hypothesized population estimator. So we can do a two-sided test when we are saying that beta 1 is not equal to the hypothesized population estimator, or we can do a one-sided test, in which case the alternative hypothesis will become either that the beta 1 is less than the hypothesized population estimator, or beta 1 is greater than the hypothesized population estimator. So both of these will be possible when we are doing the one-sided test, but there has to be some sort of underlying economic theory which will guide us towards a two-sided or a one-sided test. In most scenarios, we'll be fine with doing a two-sided test, because there's no strong theory, economic theory in most cases, which tells us that something has to be greater or less than the other. Alright, so how do we actually calculate the t-stat? So the t-stat will be calculated pretty much the same way when we were doing the hypothesis testing for the mean. So estimator minus the hypothesized value of the estimator divided by the standard error of the estimator, where the standard error of the estimator is the square root of an estimator of the variance of the estimator. So there is a formula for calculating the standard error, and we will take a look at that later on in the next couple of slides. So like I said before, when we were doing the testing, the hypothesis testing for the mean of y, we were using this formula over here, and through this formula we were calculating the t-stat, in which y bar was the sample mean minus the hypothesized population mean divided by the standard error. So similar to this calculation of t-stat, we have the calculation of t-stat in the case of hypothesis testing for beta 1. So we have the sample beta 1, we have the beta 1 hat, which is from the sample, and this is actually calculated from the OLS analysis from the regression, minus the hypothesized population estimator divided by the standard error of beta 1 hat, where standard error of beta 1 hat is equal to the square root of an estimator of the variance of the sampling distribution of beta 1 hat. So formula for standard error of beta 1 hat, how do we calculate that? So first we need to calculate the variance of beta 1 hat, and we will do that with this formula. So remember, there's a logic to, there's some sort of an intuitive logic to why this formula makes sense, and we took a look at that in the previous chapter, but once again I will kind of summarize this. So if you look at this, if you expand this term in the numerator, you can actually get variance u multiplied by variance xi minus ux. So if you think about this, variance ui, the variance of the error term or the variance of the residual, is in the numerator, which essentially means that if there is higher variance of the error term, it will lead to a higher variance in beta 1 hat. And that actually makes sense, because if there's huge differences in the estimated and the actual y's, it would mean that there's high variance in our estimator beta 1 hat. Similarly, if you take a look at the denominator, we actually have the variance of x over here. So if the variance of x is higher, it would mean that the variance of beta 1 hat will be lower. And that actually also makes sense, because if there is a greater spread in the values of x, it will be easier for us to draw a line of best fit through that scatter plot. If the variance of x is lower, it would give us less accuracy when we are drawing the line of best fit through the scatter plot. So that is how I make some intuitive sense out of this formula for the variance of beta 1 hat. So once we actually calculate the beta 1 hat, then we can actually also calculate the standard error of beta 1 hat. So the estimator of the variance of beta 1 hat replaces the unknown population values of sigma v square and sigma x square by estimators constructed from the data. So how do we calculate these the variance of beta 1 hat? So you have the estimator of sigma v square. Once again, sigma v is equal to xi minus mu x multiplied by ui, and that is what we have over here. So this becomes the estimator of the variance of v divided by the estimator of the variance of x, and that is what we have over here. So this is how we will calculate the variance of beta 1 hat. And when we calculate the variance of beta 1 hat, we will simply have to take the square root of that to actually get the standard error of beta 1 hat. So like this says over here, this is a bit nasty, and most often you won't be actually calculating this on your own, because you'll be working with some sort of statistical software. STATA, for example, if you're working with STATA will actually calculate the standard error of your estimator on its own, so you won't need to actually do it by hand. So the numerator estimates variance of v and the denominator estimates variance of x. So I've already explained why this kind of makes intuitive sense as to why these two terms, the role that these two terms play in the calculation of variance, and how these will affect the number that we get for the variance of beta 1 hat. So why are the degrees of freedom adjustment n-2? Simply because we are estimating two estimators, beta naught hat and beta 1 hat, and that is why. So the more the number of estimators that we actually estimate, the higher the number of degrees of freedom that we lose. So in this case, we are losing 2 degrees of freedom. So that's why n-2 is the degrees of freedom that we have. Alright, so to construct the t statistic, then we again have this formula over here, beta 1 hat minus the hypothesized estimator, value of the estimator, divided by the standard error of beta 1 hat. And if we plug in all the numbers over here, we can actually calculate the t stat, and we will reject the null hypothesis if the t stat that we calculate through this formula is either greater than 1.96 or it is less than minus 1.96. Now, how do we get this value of 1.96? This was described in one of the earlier chapters. This is the value of this is the t value for 5% significance level, which basically means that 1.96 will correspond to a probability of 2.5 on the right hand side, and minus 1.96 will correspond to a probability of 2.5% on the left hand side of the standard normal distribution. So the p-value is basically the probability that your t, so this t is actually the t which is the cutoff t, which is the probability of 1.96 in this case. So what we are trying to see is that if this probability of which corresponds to a t-value of 1.96 is like whether this probability is greater than the probability which corresponds to the t actual, which will be calculated by plugging in the numbers over here. And if that is the case, we will fail to reject the null hypothesis. But if that is not the case, if this probability is sorry, actually I might have said it wrong. So if this is higher than this probability, then it would mean that we will reject the null hypothesis. But if this probability is lower than this probability, then we will actually fail to reject the null hypothesis. And obviously this probability of the t will be determined by the level of significance that we choose in our analysis. If we are choosing 5% level of significance, then we are looking at the probability corresponding to the t-stat of 1.96 and minus 1.96 on both ends. So this procedure relies on the large n approximation that beta 1 hat is normally distributed. Well, whenever the sample is larger than 50, we are confident that the t distribution actually is very similar to the standard normal distribution, and that is what we actually use to calculate the probabilities. So sticking to the same example over here, we are looking at how the test scores change with the student-teacher ratios. What we find is that we have a beta naught, which is a positive number, and we have beta 1 hat, which is minus 2.28. So this negative coefficient basically means that when student-teacher ratio goes up, this actually affects the test scores, the average test scores in the school negatively. Kind of makes sense as far as our economic theory goes underlying this relationship. So if you look at the standard errors of beta naught hat and beta 1 hat, they can be calculated by the regression software that we are using. In my case, I was using STATA, for example, and these come out to be 10.4 in the case of beta naught hat and 0.52 in the case of beta 1 hat. So how do we do hypothesis testing given these standard errors and given the coefficients that we have calculated, the beta naught hat and the beta 1 hat? So for example, if we are testing that our population estimator is actually equal to 0. So in that case, our hypothesized population estimator becomes 0, which means that when we plug in the numbers over here, we have beta 1 hat, which comes from over here. So this is minus 2.28 minus 0, which means this is our hypothesized population parameter. Population estimator. So why will we use 0 as the most common hypothesized estimator of population? Because as researchers, we are mostly interested in rejecting the null hypothesis that there is no relationship between your x and y variables. And no relationship between x and y basically means that the coefficient of STR, when we are regressing STR over test score, will be 0. So that is what we are actually testing for. So when we plug in the numbers over here, we have minus 2.28 minus 0 divided by 0.52, which is the standard error of beta 1 hat, and we get a t-stat of minus 4.38. So even if we use the 1% level of significance, the two-sided significance level comes out to be, the t-stat for both sides come out to be 2.48, meaning 2.48 positive and minus 2.48 negative. So given this t-stat that we have calculated, by plugging in the numbers, we can easily reject the null hypothesis over here, because minus 4.38 is less than minus 2.58. So we can reject the null hypothesis in this case, that there is no relationship between student-teacher ratio and test score at a significance level of 1%. Alternatively, we can also compute the p-value. How do we do that? So this actually shows us the standard normal table. So our t-stat comes out to be minus 4.38 over here. So if you look at this, this is definitely less than minus 2.58, which is the cutoff of the for the 1% level of significance. So in this case, if we actually calculate the probability corresponding to the t-stat of minus 4.38, it actually comes to be about 0.00001, which is a very low probability, which once again means that we can reject the null hypothesis that there is no relationship between student-teacher ratio and average test scores. So very similar to the idea of hypothesis testing for means and confidence intervals of means is the idea of confidence interval for beta 1. So how do we do that? So recall that 95% confidence can be defined in two ways, right? So the first one is that the confidence interval will basically tell us the set of points that cannot be rejected at the 5% significance level. So if, for example, we are testing for different hypothesized population estimators, we don't have to calculate the t-stat of each of those hypothesized population estimators. The easier way to go about it would be to actually calculate the confidence interval, and with that confidence interval it will be way more easier to see actually whether our hypothesized population estimator lies within that confidence interval or not. If it lies within that confidence interval, we will fail to reject the null hypothesis. If it does not lie within the confidence interval, we will reject the null hypothesis at the 5% level of significance. That is, if we are actually calculating the 95% confidence interval. The other way of looking at it is a set valued function of data that contains the true parameter value 95% of the time in repeated samples. So in simpler terms, what we can say is that we are 95% sure that the true population parameter or the true population estimator lies within this confidence interval. So because the t-statistics for beta 1 is distributed normally in large samples, the construction of a 95% confidence interval is basically pretty much similar to what we did for the sample mean. So what we have is that we have your beta 1 hat plus minus 1.96 multiplied by the standard error of beta 1 hat, and this basically gives us the 95% confidence interval. So keep in mind that if we are not calculating the 95% confidence interval, for example, if we are calculating the 99% confidence interval, so first of all, this confidence interval will be smaller because if we are 99% sure that the true population mean lies within this range, then our range has to be larger. So sorry, if I said smaller before, I was wrong. So a 99% confidence interval will actually be larger because if we are increasing the confidence, then we are also increasing the range because we want to be more sure that the true population estimator lies within the confidence interval. But in that case, if we are looking for the 99% confidence interval, we will have to change the 1.96 to the corresponding t-stat for 99% confidence interval. So once again, sticking to the previous example of test scores and student-teacher ratio, how do we calculate the 95% confidence interval for beta 1 hat? We have the beta 1 hat, which is equal to minus 2.28 plus minus 1.96 multiplied by the standard error of beta 1 hat, and we get this range of minus 3.30 and minus 1.26. So just to double check, this range does not include 0, so we can safely reject the null hypothesis that beta 1, the true population estimator, is equal to 0. So this kind of summarizes how we can report the regression results. So this is the equation that we obtained through the regression analysis, meaning this is our beta naught hat, this is our beta 1 hat, this is our R square of 0.05. This is our standard error of regression. We already discussed what these two actually mean in one of the previous lectures. So if you're reporting the standard errors, the logical and the consistent way of reporting those would be right under the coefficients that you have calculated through the OLS analysis. So if this is beta naught hat, the standard error of beta naught hat can be reported directly below it in parentheses, and it is 10.4. Similarly, for the case of beta 1 hat, the standard error can be reported right underneath it. So if you report the regression results while giving all of this information, this gives the reader a very good idea of what the results are, how powerful the results are, how much do they make sense, how significant they are, and everything else that goes with assessing the results of OLS or regression analysis in general. So this is an output which is generated through STATA, and this is just to show how different how all of these different numbers which are reported over here are actually calculated or reported in the STATA output. So obviously we have the constant, the beta naught hat, which is 698.933, reported over here next to constant. Then we have the standard error of beta naught hat, which is 10.4, which can be reported over here as well. Then we have the coefficient for student-teacher ratio, which is basically our beta 1 hat, which can be reported over here. And then we have the standard error of beta 1 hat, which is the same, reported the same over here. Our R square of 0.05 is reported over here in the STATA output, and our standard error of regression of 18.6 is actually reported over here. Now, the t-stat that we calculated before of minus 4.38 will also be given to you in the STATA output right over here, and the corresponding value of probability that we also showed in one of the previous slides is also given over here. And the same thing will be done for beta naught hat as well. The t-stat and the corresponding probability is given over here. The last thing, the 95% two-sided confidence interval is also given for both beta 1 hat as well as beta naught hat. So the summary, to summarize all of this that we have covered so far, OLS estimators, beta naught hat and beta 1 hat can be estimated through OLS analysis, and they have approximately normal sampling distributions in large samples. So we can also do testing. We can do hypothesis testing, and the usual null hypothesis that we test against is that the hypothesized population estimator is equal to 0. We can obviously also calculate the t-stat given this formula, and we can also calculate the corresponding p-value of the t-stat that we calculate. We can once again also calculate the confidence intervals, 95% confidence intervals, 99% confidence interval, and any sort of confidence interval. Only this 1.96 will change to 2.58, for example, in the case of 99% confidence interval. So far what we have looked at is how regression analysis is done when x, our right hand side variable, our independent variable, is a continuous variable. Now x can also be a binary variable. Now what does that really mean? So binary variable takes only two values. That's why it is called binary variable. Sometimes it is also called a dummy variable. So what might be some examples of a binary or a dummy variable? So for example, if you are looking at small class size, we can say x is equal to 1 if the class size is small, and x is equal to 0 if the class size is not small. If we are taking a look at how income changes with sex, we can say x is equal to 1 if the sex is female, and x is equal to 0 if the sex is male. Similarly, we can say if we are looking at the effect of an experimental drug, we can say x is equal to 1 if treated, and x is equal to 0 if not treated by the experimental drug. So these are some of the examples that I came up with when looking at the example of binary variables. Obviously, there can be tons of other examples, but what is important to understand over here is that so far we have been looking at the slope of beta 1 hat. The slope beta 1 hat, but in the case of binary variables, the slope does not really make sense because x only takes two values, usually 0 or 1. So we'll have to interpret the binary regressor a little bit differently. So this is the example of a regression equation in which x is a binary variable. X takes only two values, 0 or 1. So if that is the case, and sticking to the previous example of student-teacher ratio and test scores, let's suppose that we say that x is equal to 1 when student-teacher ratio is lower, and x is equal to 0 when student-teacher ratio is higher. So obviously, what does high or low student-teacher ratio mean? Obviously, we will have to come up with a cutoff for what low student-teacher ratio is and what high student-teacher ratio is. For example, let's suppose we use the cutoff of 20. So anything below 20 means low student-teacher ratio, and anything more than 20 means high student-teacher ratio. If that is the case, then when x is equal to 0, meaning when we have higher student-teacher ratio, our equation, estimated equation, becomes yi equals to beta naught plus ui. And why is that the case? Because if we are substituting x equals to 0 over here, this whole thing will become 0. So the mean of yi then becomes beta naught. Why is that the case? Because the expectation of y given x, given any x, is actually equal to 0. And this can actually be utilized. So for example, if we are taking the expectation of y given any x, it would mean that we are also taking the expectation of u given any x. And we already saw that the first assumption of OLS is that the expectation of u given any x is actually equal to 0. So utilizing that assumption over there, we can basically make this expectation of u given any x equals to 0, which would mean that the expectation of y given x equals to 0 just comes out to be beta naught. So using a similar kind of analysis, when we plug in x equals to 1 over here, and we also utilize this the first assumption that expectation of y given x is equal to 1 would actually be equal to beta naught plus beta 1, and once again we are taking advantage of the first assumption of OLS, that expectation of u given x equals to 1 will also be 0. So when the expectation of u given x equals to 1 will become 0, it would mean that expectation of y given x is equal to 1 will simply become beta naught plus beta 1. So another way of looking at it would be that the effect of higher student-teacher ratio on test scores will be beta naught, and the effect of lower student-teacher ratio on test scores will be beta naught plus beta 1. So if someone asks you, like, what is the actual difference between the average test scores between classes of low student-teacher ratio and high student-teacher ratio, you will do beta naught plus beta 1 minus beta naught, which will come out to be just beta 1, right? So that beta 1 basically tells us, or the beta 1 over here basically tells us how much difference there is between the average test scores between classes of high student-teacher ratio and low student-teacher ratio. Alright, so just like I said before, our D, the dummy variable, is equal to 1 if student-teacher ratio is less than or equal to 20, and it is equal to 0 if student-teacher ratio is greater than 20. So the numbers that we get for this analysis is that beta naught comes out to be 650, and beta 1 hat, sorry, beta naught hat comes out to be 650, and beta 1 hat comes out to be 7.4. So what this simply means, if we go back to the previous slide, simply means that the effect of x when x is equal to 0 is beta naught. So in this analysis, x is equal to 0 for the case of high student-teacher ratio. So for classrooms with high student-teacher ratio, the mean test score is 650. And for classrooms with lower student-teacher ratio, the mean test score will essentially be 650 plus 7.4. And you can see this over here in this analysis. If we'll take a look at the average score of smaller class size and larger class size, this is what comes out to be in the summary statistics table. So if we do a difference in means, so remember that we can also do tests of difference in means for subsamples. So for example, if we are doing that, the standard error becomes this pooled variance over here, and using that, this standard error of difference in means and the actual difference in means, we can basically do a similar kind of t-test that we actually covered in one of the earlier chapters. So to summarize all of this, beta naught is the mean of y when x is equal to 0, and beta naught plus beta 1 is the mean of y when x is equal to 1. So the difference in group means is actually just beta 1, which means basically that that is the difference in mean between groups x equals to 1 and group x equals to 0. So t-statistics and confidence intervals, even in the case of binary regression, will be done in the same way. And obviously, just like I said in the previous slide, this is another way to do difference in means analysis. So when we are doing the difference in means analysis, we basically do a t-test for difference in means between two subsamples. And if we do a binary regression with only one variable, that is essentially what we are doing. Alright, so next we come to the problems of heteroskedasticity and homoskedasticity assumptions. So what does that really mean? What are the consequences of homoskedasticity, and what are the implications of heteroskedasticity when computing standard errors? So what do we mean by homoskedasticity, first of all? So what we mean is that the variance of u given any x should be equal to x, should be a constant number. So if x is changing, the variance of u should remain the same. So remember that the first OLS assumption is that the expectation of u given x should be equal to 0. But now we are actually making a stricter assumption, and we are saying that the variance of u given any x should be a constant number. It should not change with x. So if that is the case, if this assumption holds, then what it means is that then our errors are homoskedastic. If this assumption does not hold, then it means that the residuals or the errors are heteroskedastic. Alright, so the standard error when group variances are unequal is actually calculated using this formula, and the standard error when group variances are equal is actually calculated using this formula. And obviously the SP over here is calculated using this formula over here. So if we are assuming equal group variances, we are basically looking at the case of homoskedasticity. If we are looking at unequal group variances, we are looking at the case of heteroskedasticity. So homoskedasticity or heteroskedasticity can be better seen graphically. So what we have over here is the distribution of the residuals or the error term when x is equal to 15, when x is equal to 20, and when x is equal to 25. X in this case is our student-teacher ratio, and we are taking a look at the relationship between student-teacher ratio and test scores. So as you can see, the distribution actually changes. The distribution of U changes given the values of x. So when x is 15, the distribution is tighter. When x is 20, the distribution is slightly wider. And when x is 25, the distribution is the widest, the distribution of U. So if that is the case, it basically means that expectation of U given x is not constant given all x's. So the variance is actually increasing with x in this case. So the variance of U depends on x, which simply means that this is the case of heteroskedastic error term. This can also be seen in the case of years of the relationship between years of education and average hourly earnings. So if you look at the distribution of error term, we can see that the distribution of error terms is tighter at the lower end of the distribution of years of education, but at the higher end of the distribution of years of education, the distribution of the error term becomes wider and wider. So this is also the case of heteroskedasticity. Now this is the case of the relationship between student-teacher ratio and test scores. As you can see, the distribution of U, I mean, it's hard to say whether this is the case of heteroskedasticity and homoskedasticity, because the distribution is does not really become wider or smaller, or at least does not look wider or smaller visibly as x changes. But as far as assuming heteroskedasticity for a given data is concerned, I would say that the safe thing to do is to always assume heteroskedasticity in the data, and that basically solves a lot of problems, and that makes our estimation of the estimators beta naught hat and beta 1 hat accurate for most cases. So recall that the three initial assumptions of OLS are as follows, and I have already kind of summarized what these are. So now, given the concerns for heteroskedasticity, we will add this assumption over here that the variance of U given x is constant, and that would mean that the fourth assumption is that the error term is homoskedastic, that there is no heteroskedasticity. So what if the errors are in fact homoskedastic, right? Although the chances of that given any sort of data is very low, because there's usually enough reason to assume heteroskedasticity because of the underlying economic theory guiding our data. But for example, if what will actually happen if in fact errors are homoskedastic? So if that is the case, you can prove that OLS has the lowest variance among estimators that are linear in Y, and this result is basically called the Gauss-Markov Theorem. Now the actual Gauss-Markov Theorem is too dense to actually show over here, and if anyone is interested, they can actually look at the appendix in the book. So the formula for the variance of beta 1 hat and the OLS standard error simplifies to this general formula over here, and I've actually already explained what intuitively what the variance of U and the variance of X actually affect, and how these two variances affect the variance of beta 1 hat. So if anyone is interested in looking at the Gauss-Markov Theorem, I encourage them to go to the appendix of the book and actually take a look at what that really means. But it simply means that the estimator calculated from the OLS regression will have the lowest variance among all possible estimators. And that is essentially what we are after, for efficiency reasons. So given that, the homoskedasticity-only standard error formula becomes this. Now, the standard error of beta 1 hat that I proposed to you guys earlier in the lecture was actually a heteroskedasticity, was basically controlling for heteroskedasticity. So what it means simply is that if we find that our data is heteroskedastic, then we can use that initial formula for the standard error of beta 1 hat to do hypothesis testing and to also calculate the confidence interval. But if we actually find that our errors are homoskedastic, then we can actually get away with using this formula for the standard error of beta 1 hat. But this formula will not be applicable to calculate for calculating standard errors when there is heteroskedasticity present in the errors. So now we have two formulas for standard error of beta 1 hat. Now which one to use is obviously a valid question. So the homoskedasticity-only standard errors will be calculated when the errors are actually homoskedastic, and there is a good reason for us to believe that the errors are homoskedastic. That will be the only reason to actually use that formula. The usual standard errors is conventional to call those errors heteroskedasticity-robust standard errors. So the main advantage of the homoskedasticity-only standard error is that the formula is simpler, but obviously the biggest disadvantage is that if there is heteroskedasticity present in the data, the standard errors that you calculate will be wrong, which would mean that the hypothesis testing that you do for the estimator of beta 1 hat and beta naught hat will also be incorrect. So what are the practical implications then? The homoskedasticity-only formula for the standard error of beta 1 hat and the heteroskedasticity-robust formula differ, so in general, you get different standard errors. So homoskedasticity-only standard errors is usually the default setting in most regression softwares. That is also the case in the case of STATA. So you have to actually write comma robust at the end of every regression command for STATA to calculate the heteroskedasticity robust standard errors. And if you don't do that, then the standard errors that are calculated will be wrong, and in that case the significance level of the coefficients that you're calculating will also be wrong. So this is the example of using the comma robust at the end of the regression command, and when you do that, you get robust standard errors, and these standard errors are actually controlled for heteroskedasticity. So this is always the better option. So whenever you are doing any sort of regression, just type in blindly comma robust at the end of that regression in order to just deal with this problem once and for all, and don't really worry about whether the data is homoskedastic or heteroskedastic, because what happens is that if there is actually heteroskedasticity, then the heteroskedasticity robust standard errors will be very different than the ones that are calculated from the homoskedasticity standard errors formula. But if there is no heteroskedasticity, then the standard errors calculated from both the formulas will be pretty much the same. So actually you are in a better position already if you use comma robust, whether there is heteroskedasticity or whether there is reason to believe that there is homoskedasticity in the errors. So that is basically the bottom line, that the two formulas basically coincide when n is large in the special case of homoskedasticity. So just always use heteroskedasticity heteroskedasticity-robust standard errors in order to avoid any sort of problem with the interpretation of your beta 1 hat and beta naught hat. So some additional theoretical foundations of OLS. We have already learned a great deal about OLS. OLS is unbiased and consistent. We have a formula for heteroskedasticity robust standard errors, and we can also construct confidence intervals, and we can calculate T statistics. So OLS is basically the go-to for regression analysis in most disciplines, and that is simply because a lot of people understand it, a lot of people have used it before, and it is essentially the language of regression analysis. So you will only move from OLS if actually it adds to your regression analysis, and if there are some violation of the assumptions of OLS if you are using your data. If that is the case, then you will move to some other forms of some other regression techniques. Well, still you may wonder that is this really a good reason to use OLS, because I mean, just because everyone is doing something does not really mean that you should also do that. And also, I mean, how are you sure that the estimator, the variance of the estimator obtained from OLS has the smallest variance? And also, what happened to our old friend, the student T distribution? So the answer to your concern about OLS is that if we add these fourth and fifth assumption to the list of assumptions already existing for OLS, then we are actually making the assumptions more restrictive. So what that simply means is that these conditions will apply to fewer cases in practice. So what it means is that whenever you are actually fulfilling all of these assumptions and you are using OLS, it would mean that you will have more confidence in your estimators of beta 1 hat and beta naught hat. So if any of these assumptions is violated, it pretty much means that you should not use the OLS method. So under the extended OLS assumptions of 1 to 4, which were highlighted in the previous slide, beta 1 hat has the smallest variance, and once again I encourage all of you to go and see the Gauss-Markov Theorem, which basically shows why that is the case. And as far as the efficiency of OLS is concerned, all 5 of the OLS assumptions, including the assumption that the errors are distributed normally, would basically signify that beta 1 hat has the smallest variance of all consistent estimators. And this is an amazing result because if the errors are homoskedastic and normally distributed, then OLS is actually a better choice than any other consistent estimator. So basically you don't have to deal with any other sort of advanced regression analysis if all 5 of these assumptions actually hold for your data. But if anything else is violated, if any of these assumptions is violated, then you have to either use some other regression technique, or you at least have to use heteroskedastic robust standard errors. Some not so good things about the OLS. Obviously, we have highlighted all the positive things. The Gauss-Markov theorem really isn't that compelling, because what are the downsides of that? The downsides is that the condition of homoskedasticity often does not hold. So homoskedasticity is a truly special condition which will be very hard to find essentially in real world data sets. So when that is the case, then obviously one of the assumptions of the Gauss-Markov theorem does not hold. The other thing is that this result is only for linear estimators. So only a small subset of estimators will be linear in the population. So more often than not, every estimator or any sort of beta 1, the population estimator, should not be linear, because relationships change with increases in x and y, which simply means that it's very hard to find a truly linear relationship in real life. Also, OLS is more sensitive to outliers than some other estimators, and if that is the case, if you find that your data set has a lot of outliers, then OLS might not be the it might not be the best estimator, because the variance of beta 1 hat that you obtain from OLS when you have a lot of outliers will not be the smallest variance. So there might be other estimators out there which will have lower variance for than the beta 1 hat obtained through OLS. And one such estimator is the least absolute deviation estimator, and this is basically we basically do a minimization problem on yi minus beta naught plus beta 1 xi. Obviously this will not be covered in this chapter in detail, but just wanted to point out that if your data suffers from very high or very huge outliers, then OLS might not be the best estimator, and an estimator like least absolute deviations estimator might be a better estimator, because the variance of the beta 1 hat obtained through this estimator might be lower than the one obtained through OLS. So once again, to summarize all of this, the following are the 5 assumptions of OLS. So we have basically extended the assumptions by adding assumption number 4 and assumption number 5. If all 5 assumptions hold, then we can say that beta naught hat and beta 1 hat are normally distributed for all n. And we can also say that the t statistic has a student t distribution with n minus 2 degrees of freedom, because once again we are estimating 2 estimators, beta naught hat and beta 1 hat, so the number of degrees of freedom becomes n minus 2 rather than n. So why n minus 2? I already explained that. So for n is less than 30, the t critical values can be very different from the critical values obtained from the standard normal table. But that is not the case for n greater than 50. When n is greater than 50, pretty much the t values, the critical values obtained from the standard normal table and from the t distribution table, the student t distribution table, pretty much converge, which means that for larger samples, and not really like super large, like for samples larger than 50, you can simply use the standard normal table to calculate to calculate the probability corresponding to the t-stat that you calculate. So practical implication is that if n is less than 50 and you really believe that for your application the error terms is homoskedastic and normally distributed, then use the student t distribution instead of the standard normal distribution. But if that is not the case, then you can simply go with standard normal distribution, meaning if your n is greater than 50 and you have reason to believe that your error terms are not homoskedastic, they are in fact heteroskedastic. And just like I pointed out earlier, in most econometric applications, there is no reason to believe that your error term is homoskedastic and normally distributed. So so that is why it's always better to go with the standard normal distribution. And obviously in modern applications, whenever you're out there collecting data, you normally don't collect data sets of just 50 observations. So once again, if your n is greater than 50 and you have reason to believe that that you don't have homoskedastic errors, which means you have heteroskedastic errors, then you can simply use the standard normal distribution, because you will be utilizing the law of large numbers and the central limit theorem, which we have previously covered. So summary and assessment. So the initial policy question, for example, if the question that we were interested in was that suppose new teachers are hired so that student-teacher ratio falls by 1 student per class. Now what will be the effect of this decrease in student-teacher ratio on student test scores? Now obviously if you are a policymaker, all of these kind of decisions are hard to make, because like hiring new teachers costs a lot of money. So you want to be sure whether you have confidence in the estimator of the regression analysis that you have done. So the answer then becomes that the numbers that we calculated for beta 1 hat and beta naught hat, are they convincing enough to answer this question or not? Well, not really, because we have omitted a lot of the variables from our analysis which can also impact the test scores. Now, some of those variables might be the income of the households which is served by the school, right? Another variable might be the quality of the teachers. Another variable might be the facilities available at the school, right? So all of these, there might be like 1,000 other variables which can impact the test scores of the student. So unless we also control for those variables, we will not really get an accurate measure of beta 1 hat, which is the effect of student-teacher ratio on the test scores of students. And that is what we'll be doing in the next chapter. We will be moving to multivariate regression analysis, and but this basically concludes our lecture on regression with a single regressor and hypothesis testing and confidence intervals for a single regressor. So until next time, take care, and I hope this lecture helped. So thank you for watching, and happy regressing.